One thing right now more than 5 billion people are using the internet over the world. But did you know that entire system runs on a single protocol that was invented 50 years ago? The protocol is IP protocol. In today's video, we are going to understand this protocol and we will see what are the concepts we are going to learn. Let's look at the today's agenda. First, I will introduce you to IP. Once you understand what is IP, then we look at the IP header. We are going to cover each and every field involved in the IP header. After that, we will see how IP works in the real day. Finally, we will explore the different IP versions and IP classes. So this is all about the today's agenda. Make sure that you watch the video till the end. By the end of this video, you will clearly understand how IP is and how IP works in the real time. Okay. So before we start with our first topic, if you are really curious about the history of IP, I have already covered in my video of the history of the internet. That is my very first video in my computer network playlist. If you haven't watched that video yet, I highly recommend you to watch the video if you are really curious about the history of the internet. Alright, let's start with our first topic, introduction to IP. What is IP? You might have heard this term IP. But have you ever wondered how IP works in the real time? What are the concepts involved in the IP? What is it? What does it really do? IP stands for Internet Protocol. It is the primary communication protocol that makes sure that the devices can talk each other over the internet or the different network. Okay? So if you observe, every device is connected to the internet, it is assigned to the one IP. The reason we assign the IP address is very simple. Whenever you access something on the online, your IP address acts as an identity of your device. It tells that the data can be sent and received from the correct device. For example, in your home, you may use laptop, tab or mobile phone. As soon as you connect to the internet, each of the devices get their own IP by using DHCP protocol. We'll talk more about the DHCP protocol in the next videos. So let's imagine if there was no IP, the device cannot send or receive the data from the internet. So this is the primary function of the IP. It enables the device to communicate over the internet. Let's take simple example to understand this better. Imagine you want to travel to the another city. What do? You go to bus station or railway station. So once you reach the bus station, you look at the board displayed on the each bus, right? So these boards tell you the destination. So you know that which bus you should take. Similarly, IP works like the destination label on the internet. If you zoom out everything, if you see from the top, right, the internet is like a huge network. The world is connected over the network. It looks like a mesh of connections. To find one specific device, we assign the unique number, that is IP address. Then only the data can be delivered correct. Now, you might think IP only handles the addressing the devices, but no, it does much more. Let's go step by step what IP really do. The first thing is addressing. As we discussed earlier, each device in the network gets a unique IP address. Okay, this is one of the function. The second function is packetization and fragmentation. What does it do? IP takes the data and breaks into small chunks. The small chunks we call as the packets. If you remember in the TCP, the data is divided into small segments. We call the segments in the TCP. In IP, we call them as a packets. You may have a question here. Since we are dividing the data into small chunks and also we are calling as a packet, does it have any size limit? Yes, it does. This particular size depends on the MTU. What is MTU? MTU stands for maximum transmission unit. Basically, it divides the maximum size of the single packet can travel over the network link. For example, in the Ethernet, your typical MTU size is 1500 bytes. If the packet is larger than MTU, the IP will be fragmented into small packets that fit into the MTU. Hold up. Again, I came up with another concept, fragmentation. Now, I know you might be confusing since I use 3 terms here: fragmentation, packetization, and MTU. For better understanding, let's put all this together, understand them clearly. So, when you receive the data from the upper layers, the packetization comes first. So, it takes the large chunk of the data from the transport layer that it's divided into small pieces. The small pieces we call the packets. This is a normal process of all the communication. So, we are preparing the data so that can be transmitted over the network. So, this happened for every packet. But when fragmentation happens, sometimes a router or even sender needs to split the packet into further because it is too big for the network link. How do we know that it's too big? That's where MTU comes in. So this MTU tells us the maximum packet size is allowed. If the packet exceeds that limit, it's required the fragmentation. Then IP split the packet into small fragments. Each fragment, it has own IP header that can travel independently across the network. So if we put in short, packetization is always done at the sender to prepare the data into packets. Okay, this is a normal process. So if it's happened to every packet. But fragmentation happens if the packet is larger than MTU. Okay, so we'll do one thing. Let's take simple example and try to understand in better way. It is a general example. Imagine you ordered a cake. Okay, you got a cake. Imagine this cake has a big size. What you do? You cut into slices, right? So that's the packetization. But if one slice is still too big for the plate, here the plate is represented as the MTU. What you do? You cut it again into smaller pieces. That is the fragmentation. Okay, so this is all about the fragmentation, packetization, and MTU. Now move to the another function, that is routing. So once the data is split into the packets, IP decides the best path for these packets to travel across multiple networks. This is done with the help of routing protocols. We do have the different routing protocols: RIP, OSPF, and BGP, and using routers. Okay, so this will find the best path to reach some source to the destination. This is also one of the function in the IP. Now move to the encapsulation. So we already covered what is encapsulation in the OSI. If you haven't watched that video, please watch the video OSI model. Okay, IP also encapsulates the data coming from the higher layers like TCP, UDP, or HTTP. So what it will do? It wraps the data and assign the correct IP address to ensure that reach the right destination. So in short, IP is not just about the addressing, it is all about the packetization, routing, encapsulation. So these are the main functions of the IP. Now let's understand IP header. What is an IP header here? So this IP header is a controlled information that sits in center of the actual data in every packet. So how it looks like? Here is the IP header, here is the data. So it stores the necessary information needed to deliver the packet correctly. Okay, so let's discuss each field one by one, whatever we do have in the IP. Before we understand these fields, let's understand the IP header size. IPv4 header is usually 20 bytes minimum, but it can go up to 60 bytes with an option. Okay, now we jump into the fields. The first one is version. Here we do have two versions of the IP. The first one is IPv4 and second one is IPv6. I won't cover much here since we do have a separate topic in this video on the IP versions and IP classes. We'll discuss more about these versions later. So this particular version field tells that which version the packet is using, either IPv4 or IPv6. Okay. The next one is header length. What does it do? What it defines? It defines the length of the header itself. As we discussed, the minimum length is 20 bytes and the maximum is 60 bytes. So it tells the receiver how much of the packet belongs to the header. Only it tells the length of the header itself. Okay. So this is all about the header length field. Now let's move to the next field, which is TOS. What is it? What does it do? TOS stands for type of service. Basically, it tells the network how packets should be handled. Originally, TOS was designed for different purpose. The purpose is to indicate the priority and the quality requirements of the packet. Okay. So now we'll discuss about the original TOS purpose, which is 8 bits field. Okay. So this divided into different parts. The first part is precedence. What is precedence? This precedent has 3 bits. Okay. So it's define the priority of the packet. Higher precedence means the packet is more important. Let's take example like it's a voice or critical data. So that time we use this precedence has a 3 bits. The next one is delay. Delay is the 1 bit. This is something used for low delay preferred. It is mainly important for real-time applications. Okay. So the next one is throughput. This is also 1 bit. High throughput preferred. It is used for bulk transfers. The next one is reliability. This is also 1 bit. So it is used for high reliability preferred when it's required. And also we do have the 2 bit, that is for reserved. This is not used. This is kept for future purpose. For better understanding, let's take one example. If you are making a voice call, so this TOS field could request a low delay. At the same time, if you are downloading the file, so the packet could request the high throughput. So based on these bits, the network would take appropriate action on the packet. So this was previously used, but modern use of TOS is, so this TOS has evolved. It is mainly used for 2 forms. The first one is DSCP and second is ECN. What is DSCP? DSCP stands for Differentiated Service Code Point. So this is all about the 6 bits. This is something used for prioritize the packets of the quality of the service in modern networks. The second one is ECN, Explicit Congestion Notification. If you remember, this particular flag we already discussed in the IP header. So it's indicate that network congestion without dropping the packets. Okay. So when you see TOS in Wireshark or in the network devices today, it is mainly used for traffic prioritization of the QoS, not for the old delay, throughput or reliability bits. Okay. So this is all about the TOS. It is mainly used for how you are handling the data. Okay. So now let's move to the next field, that is total length. So this particular field specifies the size of the entire packet, including both the header and data. So the maximum value can be 65,535 bytes. Okay. So in IP, we have 2 types of lengths, right? We already discussed header length. It tells the only size of the header. Now total length, the size of the entire packet, that is header plus data. Okay. So this is all about the total length field. The next field is identification. What does it do? Each packet is assigned a unique ID. So the purpose of this ID is to help the reassemble the fragments if the fragments occurs. How does it work? Let's say the packets needs to be fragmented with the size exceed the MTU size. So what we will do? The packet is divided into small fragments. So each fragment is assigned the same identification value. Okay. So when the receiver get these fragments, So this IOD helps the reassemble them correctly into the original packet, which is why we use the identification field. Okay. Now let's move to the another field, which is flags. In IP, we do use different flags to control or identify the fragmentation of the IP packets. So this is mainly used for the fragmentation. So this indicates whether the packets require the fragmentation. If it requires, once the fragmentation has started, and also it tells the what is the last fragment has been set. For better understanding, let's look at the 3 bits of the flags. We do have the 3 bits. One is bit 0, bit 1, bit 2. Bit 0, it is reserved. It is always set to 0, not used. Now, we'll discuss about the bit 1. So, bit 1 is DF. What does it do? DF means don't fragment. If it is set to 1, the packet must not be fragmented. If it is set to 0, the packet can be fragmented if needed. Okay. So, the next one is bit 2. That is MF, more fragments. If it is set to 1, there are more fragments after this one. If set to 0, this is the last fragment of the packet. You may have a question here. How we are deciding the packet should be fragmented or not? If you remember, so based on the MTU size, we will decide the packet should be fragmented or not. So this is how the fragment works. For better understanding, let's take simple example. Let's say if the packet is too large, that needs to be a fragmentation. Let's suppose it's split into 3 fragments. Now fragment 1, DF equal to 0 and MF equal to 1, which means the more fragmentation follow. The next fragmentation, the fragmentation 2, DF equal to 0, MF equal to 1, which means again more fragmentation follow. So when fragmentation 3, DF equal to 0 and MF equal to 0. So this is the last fragment. Okay. So this shows how the DF and MF bits help the network and receiver handles fragments packets correctly. Okay. So this is all about the important fields in the IP. Now let's move to the next field, which is TTL, time to link. TTL is a 8-bit field in the IP header. So this is used for limit the lifespan of packet in the network, and also it prevents from the circulating indefinitely. Let's imagine you are sending a packet device over the network. Let's assume if the TTL is not assigned, the data could end up circulating in a loop between the same devices and traveling through the same devices repeatedly. So to avoid this, we use TTL. How TTL works? So when a packet is created, so this sender assigns the TTL value. For example, 64, 128 or 255. So these values depends on the operating system. So every time this packet passes through the router at a hop, so the TTL value is decreased by 1. So if the TTL reaches the 0, before the packet reaches the destination, the packet is discarded. So this mechanism prevents the routing loops from the causing endless traffic in the internet. So here the key point. TTL does not control the delivery time. It controls the maximum number of hops. Hops here means routers or network devices. So the packet can traverse. So this is all about the TTL. The next field is protocol. So these fields indicate the which transport layer protocol is carried inside the IP packet. For example, we do have the 3 main protocols we have in the transport layer, that is TCP, UDP and ICMP. So it tells the receiver what type of data to expect. So it tells the what kind of protocol we are using in the field. Either it can be TCP or UDP. The next field is header checksum, which is an IPv4 header field. So the header checksum 16-bit field used for error checking of the IP header only, not payload. So remember in the TCP checksum, we added the checksum for both payload and data. But here it is only for the IP header. So it is verify the header the data has been not corrupted during transmission. So how it is works? So when the packet is created, the sender calculates the checksum based on the all the headers, only IP header, by using one's complement addition. So the particular value which is stored in the header checksum field. When the router destination receives the packet, it recalculates the checks. The calculated checksum matches the value in the header. The header is assumed that okay, this particular packet is correct. If there is a mismatch, the packet is discarded because it indicates that the header has a corruption. Important point you should remember here, only the header is checked, not the payload. So each time the router modifies the header, like decreasing the TTL. We all know that. So as soon as the packet received by the any router or network devices will decrease the TTL. So what it will do, it recalculates the checksum to ensure that integrity of the routing information. This is how checksum works. The next one is source IP. It is simply the IP address of the sender. It will store the sender of the IP. After that, destination IP address, which is the IP address of the receiver who is going to receive the packets. Okay. Finally, there is an option field, which is rarely used. It can be include things like a security, timestamps, or debugging information. So this is all about the IPv4 header. Now we will see the IP header in real time by using IP header CloudShark website. Okay. So let me open the packet and we will see what are the fields which we can see in the IP header. Let me open IPv4 and let me zoom in. Let me open Internet Protocol version. See, if you see here, so what are the fields we have discussed in the IP header? You can see the same fields here. Okay. So you can see the first one is version. It is showing IPv4. Then header length 20 bytes. Then you can see here type of service. Okay. So that is DHCP and ECA. Okay. Then the total length. Here the total length means header length and payload. That is 1500. Then identification. So if you remember the identification field which is used for when the fragmentation happens. So then each packet we will provide the identification number. Okay. So then you can see here flags. Okay. So the reserve bit, don't fragment and more fragments, which means we need to fragment the packets. Then you can see here time to leave, that is the 32. So each time the packets travels to the routers, this value is decreased by 1. Here the protocol we are using ICMP. Then header checksum. So the value which is stored in the header checksum. Then the source address. This is the source IP address. Then this is the destination IP address. Now let's understand how IP works in the real time. For understanding this, let's take example. That is, you are accessing a one website. To access that website, first you open your browser and type URL and hit the enter. So once you hit enter, the computer first asks the DNS resolver to resolve the domain name into the IP address. So once you got an IP address from the DNS server, then your computer creates an IP packets containing the source IP, destination IP and other fields. Okay. So this packet will be sent out to your default gateway, usually router. Okay. So once the router receives the packet, it will check the routing table to determine the next hop. Okay. So if the destination is outside your local network, so the packet is forwarded through the multiple routers across the internet. At each hop, router inspects the destination IP and decrement the TTL value as we discussed in the IP header. Okay. And forward the packet is closer to the destination using routing decisions. When the packet finally reaches the destination server, the server sees the destination IP matches its own. Then it will remove the IP header. It will only passes the payload to the appropriate protocol. That is something example TCP for web request. So now the server responds with its own packet and the process repeats the reverse direction until your computer receives the data, display the web page, since you are trying to access the web page. So this is how the IP works in the real time. Okay. So now let's see the another topic, that is IP versions and IP classes. First, let's discuss IP versions. As we discussed, we do have the two versions, right? One is IPv4, second one is IPv6. First, let's look at the IPv4. An IPv4 address looks like 192.168.1.1. It has 4 octets separated by the dots. So each octet is a 8 bits. So the total size is 32 bits. Okay. If you want to calculate the total number of possible IPv4 addresses, how do you calculate? 2 power 32. You will get a value like 4,294,967,296. Cool. It's a huge number, right? But you may have a question here. Are we using all these addresses? No. Some are reserved for the private networks and special purpose. Okay. We'll talk more about when we cover the IP classes. So this is all about the IPv4. It has 4 octets and it is each octet 8 bits. The total IP size is 32 bits. Okay. Now let's move to the IPv6. But before we move to the IPv6, let's understand why we even need IPv6 since we do have the IPv4. Right? So when IPv4 was created, the designers did not anticipate the huge growth for the internet. They didn't expect that how this internet got evolved. If you look at today, billions of devices are connected to the internet and IPv4 addresses are running out. So to solve this limitation, to solve this problem, they are introduced to IPv6. Let's understand what is IPv6 and how it is different from the IPv4. So it uses 28 bits. IPv4 uses 32 bits. Okay. So which is in a decimal format. IPv6 uses hexadecimal. Unlike IPv4, which is in a decimal format. IPv6 uses hexadecimal with the alphanumeric characters. This is separated by the colons. If you want to calculate how many total number of IPv6 we do have, that you need to do 2 power 128. So you will get a huge number that is enough for every device on the earth to have the billions of the addresses. Currently, we are still using IPv4, but IPv6 is the future purpose. Okay. So it's provide the enough address for every devices, improve the efficiency. Okay. So understand these both versions is important for networking and cyber security. So this is all about the IP versions. Now let's move to the IP classes. The first question you should ask here, what is IP class? Why do you even need it? Okay. So to answer that question, when IPv4 was designed back in the early 1980s, the internet was still new. The people who is designing, they didn't know how many devices or networks could exist in the future. So to handle this situation, they came up with a concept called classful addressing system. So what does it do? So it's organize and manage the IP address. So the idea was very simple. Not every organization needs the same number of IP addresses. A small company might need only few addresses. A large universities or government organization might need thousands or even millions of IP addresses. So to solve this problem, the IP addresses were divided into 5 classes. They are A, B, C, D, E. So which is efficiently allocate addresses based on the size of the network. Let's discuss each class with the range of the each class. Okay. The first one is class A. So it has few networks, but each network could support millions of hosts. This is mainly designed for very large organization. Okay. You may have a question here. What is network? What is host? Okay. So the network identify which network the device belongs to. Okay. So all the devices within the same network share the same network portion of the IP address. I know it is a bit confusing. For that, let's take general example and try to understand. Example is the IP address is 1.1.1.1. Okay. So since it is belongs to the class A, in class A, the first octet is the network part. Okay. Other octet which is belongs to the host, which means you will see the many hosts in the class A. If we take general example, imagine you are in a one street. Okay. So the street name equals the network. Each independent house on the street is a host. Okay. So now we'll look at the class A range. The range A starts from the 1.0.0.0 to 126.255.255.255. Subnet mask here 250.0.0.0, where the network portion is 8 bits and the host portion is 24 bits. But here you need to understand one more concept is subnet mask. What is subnet mask here? So the subnet mask is the 32-bit number, which is used in the IPv4 to help the divide the IP address into two parts, as we discussed, network portion and the host portion. Okay, so that it identifies the which network and IP belongs to and identify the which specific devices within the network. Let's take an example like 192.168.1.10. The subnet mask is the 255.255.255.0. Okay, so your network portion is here 192.168.1. The host portion is the 10. So this is how it looks like. Okay, now move to the another class, that is class B. It supports thousands of hosts, which is used for medium-sized organization like universities. The range starts from the 128.0.0 to 191.255.255.255. Since it has the two network ports and two host portion, so the subnet mask is 255.255.0.0. Network portion is the 16 bits, host portion is the 16 bits. Okay. Now class C. It supports only 254 hosts. This is commonly used for small business. This range starts from the 192.0.0.0 to 223.255.255.255. The subnet mask is here 255.255.255.0. The reason is the network portion is here 24 bits. The host portion is 8 bits. Okay. So now move to the class D. So the class D is mainly used for reserved for the multicasting. Okay. The range starts from here 224.0.0.0 to 239.255.255. Then class E. So the class E is for reserved for experimental purpose. So the range starts from 240.0.0.0 to 255.255.255.255. Okay. So this is all about the IP classes and the ranges. So far we have discussed the public IP address. Now let's look at the another important concept, that is private IP address. Why do we use? So this private IP address is reserved for use within the private network such as your home, Wi-Fi or office LAN or corporate internet. Okay. So these private IP addresses are not routable on the public internet. This means if you try to use the private IP directly to the access to the internet, it won't work because the global internet routers will drop the packets. So remember, with the private IP address, you cannot access to the internet. Then why do we use private IPs? That is the question, right? The main purpose to conserve the public IPs. Since public IP addresses are limited, if every device in the world required a unique public IP, we would have run out them long ago IP address. Okay. Instead, devices inside the network use the private IP address. If they want to connect to the internet, they use protocol like network address translation. So what it will do? The network address translation group of private IP address to map to the single public IP. So make the communication happen within the internet. Okay. So it is also ensure that the response from the internet are sent back to the correct device inside the private network. Okay. So we'll talk more about the math in detail later. But here the key part you should remember is private IPs help the conserve public IP address. And also it's provide the security. since devices with a private network that cannot be accessed directly from the internet. So that is the difference between the public IP and private IP. Okay. So if you put in short, public IPs are used for communication over the internet. Private IPs are reserved for internal communication with the private networks, are not routable on the public internet. Okay. So even private IP address are divided into some classes. Okay. So it is divided into 3 classes: class A, class B, class C. In class A, so the range starts from the 10.0.0.0 to 10.255.255.255. Then class B, 172.16.0.0. Then class B, the range starts from the 172.116.0.0 to 172.31.255.255. Then class C, the range starts from the 192.168.0.0 to 192.168.255.255. So this is all about the private IP address. You may have a question here. If I want to check my what is private IP, what is my public IP of the computer or laptop, how do I check? Okay. So if you are using Windows, you can open CMD and type ipconfig. You will see the private IP address. Okay. Since I am using Mac, let me open terminal and type ifconfig. Okay. So here you can see my private IP address. Okay. So if I want to check my public IP address, right? So there is a website. What is my IP address? See, here you can see your IPv6 public IP, and here you can see the public IPv4. So this is how you can check your private IP and public IP of your system. Okay. So that's all for the today's video. We have covered what is IP and what is IP header and how IP works in the real time. Then we have covered the IP classes and IP versions. Okay. So I will be back with another exciting topic in the next video. Until then, take care. Bye bye.